Alright, so in this video, we're going to be showing that W, which is the set of all two-dimensional vectors, x and y, so that 7x plus 5y is equal to 0, that is a legit subspace of R squared. And so if we want to show that it's a subspace of R squared, we need to show two things about it. One, that it's closed under vector addition, meaning if I pick any two vectors and I add them together, that it's still that vector is still something that lives in W. And similarly, scalar multiplication, meaning I take any one of these vectors, I scale it however I want to scale it, and the resulting thing still also lives in W. So I'm going to go ahead and start with closed under vector addition. And so we're going to let x1, y1, x2, y2 be in W. So remember the reason I'm doing it this way and not picking, say, specific choices of x and y is because we want to show that every possible sum of things that live in W also live in W. So it would be useless to just show that for two things that live in W. We want to show it for all of the x1, y1s, x2, y2s that live in W. And so I want to show what I want to show is that x1, y1 plus x2, y2 also lives in W. Alright? And something that's worth noting parenthetically is that what x1, y1 plus x2, y2 is x1 plus x2, y1 plus y2, right? And that might come in handy down the line. Now, what we know is that since x1, y1, x2, y2, let's say R and W, what we know is that they both satisfy the criteria of W's elements, meaning that 7x1 plus 5y2 is 0, and 7x2 plus 5y2 is also 0. So we are given those facts. And so now what we want to do is we want to consider x1 plus x2, y1 plus y2. Does this vector also live in W? Well, if it were to live in W, what that would mean is that if I take 7 times the x entry and 5 times the y entry, that this term here should allegedly be 0. Well, I don't know that yet. But what I do know is these two facts, right? That 7x1 plus 5y1 is 0, and 7x2 plus 5y2 is also 0. So what I can say now is that, well, what I know is that this is equal to 7x2 plus 5y1 plus 5y2, right? That is from just plain old distribution. And what I also know is that I can rewrite this grouping the ones and the twos together. And because I've already established these facts here, what I can finally conclude is that this is equal to 0 plus 0. So what I have now done is shown that 7 of the x entry plus 5 of the y entry is equal to 0. So thus W is closed under vector addition. Alright? Now we want to show that it's also closed under scalar products. Scalar multiplication. Or closed under. So to see this, what we first want to note is we let x, y, be in W, i.e. once again that we go back to condition here, right? 7x plus 5y is 0. And we claim that c times xy, or we want to show, maybe I'll use the consistent language, we want to show that cxy is also in W, right? So the way we're going to show this is we're going to recall that cxy is cxcy, and we're going to ask ourselves if this is in W. Well, if it were in W, it would satisfy the same condition, that 7 times x value plus 5 times the y value was 0. So we take 7 times the x value plus 5 times the y value, and I don't know that that's 0 yet. But I do know that I can factor out a c and have 7x plus 5y, which is perfectly fine. And then I note here, oh, I've already established that that's 0. So this whole thing is c times 0, which is 0. So what we've done is we've established that cxcy in fact satisfies the W condition. Thus, cxy is in W, and W is closed under scalar multiplication. So it's closed under vector addition. It's closed under scalar multiplication. So since W is closed under both scalar multiplication and vector addition, it is a subspace of R squared. Alright, thank you very much. See you in the next video.